Welcome to EPG Pathshala. Students, in today's module, we are going to discuss on solar radiation. Sun is the heart of our solar system and it produces enormous amount of energy by nuclear fusion. This hot body radiates the energy in the form of heat. This radiated energy reaches the earth and it is known as solar energy. It varies from place to place and time to time. In this module, we are going to discuss on this radiation spectrum of the sun and the earth. What is extraterrestrial radiation? What do you mean by solar constant? What is the basic angle between the earth and sun? How you will calculate the local apparent time? What is the angle between the incident light to the normal and inclined surface? We will also see how to find out the time for the sunset and sunrise as well as the solar day length. We will see the intensity of terrestrial radiation also. We will also discuss different measurements or how to measure this radiation and what is the need of this solar radiation data. We will also see the types of radiation, mainly the beam radiation or direct radiation and the diffuse radiation. Let's start with the radiation spectrum from sun and earth. Sun is considered as a black body which is having a high surface temperature of around 5800 degrees Celsius or 6000 degree Kelvin. The radiation spectrum consists of emission of various wavelength, but we can see that in the spectrum it is more towards the shorter wavelength. The maximum emissive power of the radiation takes place at a wavelength of 0.48 micrometer. And if you compare this with the radiation emitted from the earth, we can see that the earth is also a black body emitter and it has a surface temperature of 288 Kelvin or 15 degrees Celsius. This radiation spectrum from the earth mainly consists of emission of the longer wavelength. So, the maximum emission takes place at a wavelength of around 10 micrometer. So, if you compare this radiation from the sun and the earth, we can see that the sun's radiation is mainly consists of the shorter wavelength while the radiation from the earth is longer wavelength radiation. What do you mean by irradiance? It is the rate at which radiant energy is incidenting on a unit surface area. It is the measure of the power density of sunlight falling per unit area and time. That is the rate at which the radiant energy is incidenting a unit area. It is measured in watt per square meter. Normally the heat energy is measured in joules or the unit of power is joule per second. Irradiation, it is the solar energy per unit surface area which is striking a body over a specified time. Hence, it is an integration of solar illumination or irradiance over a specified time. That means, it is an integration of the irradiance over specified time. Usually, it may be an hour or a kilowatt day. It is measured in kilowatt hour or kilowatt day per square meter. You can calculate the irradiation if irradiance is given. For example, if irradiance is 20 kilowatt per square meter for 5 hours, the irradiation can be found by multiplying the irradiance with the time. That is 20 multiplied by 5 will give you 100 kilowatt per meter square. Now, we will see the extraterrestrial radiation. Before that, we can say that the earth revolves around the sun in an elliptical orbit and we know that the earth is closest to the sun on 2 days, 21st March and 23rd September, while it is far from the sun on 21st June and 22nd December. And if you see the mean distance of the earth from the sun, it is around 1.495 multiplied by 10 to the power 11 meters. We can say that the intensity of radiation outside the earth's atmosphere reduces with the distance and it is dependent on the distance between earth and the sun. So, the intensity of solar radiation that is reaching the earth's atmosphere is different with the square of the distance between the centers of earth and the sun. That's why the earth receives around 7% more radiation on 21st March and 23rd September as compared to 21st June and 22nd December, where the sun is more closer to the earth. So, the intensity of solar radiation keeps on changing as the earth propagates away from the surface of the sun, but the content of wavelength in the radiation spectrum remains same. Here the earth axis is tilted about 23.45 degree, or you can say roughly 23.5 degree with respect to earth's orbit around the sun. Owing to this tilting, the northern hemisphere of earth points towards sun in the month of June and it points away from the sun in the month of December. This earth axis remains perpendicular to the imaginary line drawn from the earth to the sun during September and March. The sun-earth distance varies with the earth's revolution around the sun. So, the solar energy reaching its surface also varies. Because of this revolution, the seasonal changes occur. The northern hemisphere has summer when the earth is tilting forward the sun and winter when the earth is tilting away from the sun. So, in the month of September and March, both the hemisphere, that means north and south hemisphere, are at the same distance from the sun, that is, this is mainly equinox time. They are at same distance from the sun and they receive equal sunshine. During the summer, the sun is higher in the sky while the sun is lower, that means it is far from the earth during winter for the northern hemisphere. So, the solar radiation incident on the outer atmosphere of the earth is known as extraterrestrial radiation. It varies based on the change in sun-earth distance which is arising from the elliptical orbit of the revolution of this earth around the sun. There is a term known as solar constant. It is defined as energy received from the sun per unit time on a unit surface area perpendicular to the direction of propagation of solar radiation at the top of Earth's atmosphere when Earth is at mean distance from the sun. That is the energy received from the sun per unit time per unit area which is perpendicular to the direction of propagation of solar radiation. The value of solar constant is 1367 watt per meter square. Now, the extraterrestrial radiation can be determined by using this solar constant. Ix is equal to ISE multiplied by R average by R all square, where I extent, that is the extraterrestrial radiation, is equal to the solar constant. IC is the solar constant and R average is the mean distance between the sun and the earth, and R is the actual sun earth distance, mean distance and the actual sun earth distance. So, we can give this equation as extraterrestrial radiation is equal to 1 plus 0.033 cos 360 n by 365 where n is the number of days. It should be counted from 1st January and it is reported as, or it is expressed as watt per meter square. If you know the actual sun earth distance, you can calculate extraterrestrial radiation. Now, what is terrestrial radiation? So, extraterrestrial radiation is the solar radiation reaching the earth's surface. Now, when the radiation passes through the atmosphere, it is subjected to different mechanisms like absorption, scattering, depending upon the conditions present in the atmosphere. We have seen the earth budget. Here mainly absorption, scattering and reflection happens, and also some re-radiation from the earth's surface also happens. So because of the presence of some molecules and the dust particles present in the earth's surface, the complete amount of solar radiation is not reaching the earth's surface. Therefore, solar radiation or the intensity of radiation is reduced during its passage. The solar radiation that reaches earth's surface after passing through earth's atmosphere is called terrestrial radiation. Here, from extraterrestrial region, the solar radiation reaches earth's surface in two ways. A portion of the sun's radiation or solar radiation travels through the earth's atmosphere and it reaches directly, which is known as direct or beam radiation. The remaining part of the solar radiation is scattered, reflected back into the space or absorbed by earth's atmosphere. A part of this radiation reaches the earth's surface. This radiation which reach the earth's surface by means of scattering and reflecting, that is re-radiation, is called diffuse, also known as sky radiation. So, you have beam radiation and the diffuse radiation. So, the sun's rays reaches the earth in two ways, either in the form of direct radiation, that is beam radiation, or in the form of diffuse radiation. The diffuse radiation takes place uniformly in all the direction. Now, what is this beam radiation? We have seen that the solar radiation along the line joining receiving point and the sun is called beam radiation, and this radiation has a unique direction. It falls in a single direction, while diffuse radiation is the solar radiation which is scattered by the particles in Earth's atmosphere, and this radiation does not have any unique direction. That means it can take place uniformly in all the direction, and the intensity does not change with the orientation of the surface. The beam radiation depends on the angle of incident on the surface, and its intensity is maximum when the solar radiation is falling normal to the surface. The solar radiation propagating normal to its direction is normally specified by IN. The total or global radiation at any point on Earth's surface is sum of the beam radiation and diffuse radiation. So, total radiation is equal to beam radiation plus diffuse radiation. Air mass. The radiation reaching Earth's surface depends on atmospheric condition and depletion and solar altitude. So, the air mass is the ratio of path length through the atmosphere which the solar beam actually traverses up to Earth's surface to the vertical path length through the atmosphere. At sea level, the air mass is unity, that is 1 when the sun is vertically in the sky, that is it has an inclination angle of 90 degree. So, the air mass denoted by M is equal to path length travelled by beam radiation divided by vertical path length of the atmosphere. You can see in this figure AC, the air mass is equal to AC by AB, which can be written as cosec alpha, and that is equivalent to sec theta, where alpha is the inclination angle formed and the theta z is the zenith angle. So, if you know either the inclination angle or the zenith angle, you can find out the air mass, which is the ratio of the path length travelled by beam radiation to the vertical path length of the atmosphere. If the M is equal to 1 when theta is equal to theta z, zenith angle is 0. And M is equal to 2 when theta z is equal to 60. So, by that way you can find out the air mass, the relationship between, this is the relationship between the air mass and the inclination angle or the zenith angle. Now, coming to the latitude and longitude. Any location on the earth can be found out by knowing the 2 points, that is latitude and longitude. If you know the latitude and longitude, you can find out the position or the point at which that location is situated on the earth's surface. So, longitude is the vertical lines of constant, the vertical lines, its imaginary line, and latitude is the horizontal, it represents the horizontal line, and it is the mean distance or the distance from the equator. And each degree of latitude is about 111 kilometer apart. Now, we will see what are the angles which are used in solar radiation analysis. We have seen that latitude is important, that is known as angle of latitude or lambda. The latitude of a location on Earth's surface is the angle made by radial line joining the specified location to the center of the Earth with the projection of this line on the equatorial plane. So, the latitude at equator is 0 and at pole it is 90 degree. Then the second angle is declination angle denoted as delta, and it is the angle made by line joining the centers of sun and earth with the equatorial plane. The angle of declination differs when the earth revolves around the sun. It has a maximum value of 23.45 when earth achieves a position in its orbit corresponding to 21st June and has a minimum value of minus 23.45 when earth is in orbital position corresponding to 22nd December. So, the angle of declination taken positive when it is measured above the equatorial plane in the northern hemisphere, and it is denoted as delta is equal to 23.45 multiplied by sine of 360 by 365 into 284 plus n, where n is the number of days from the 1st January. So, this is the declination angle. This angle is made by line joining the centers of earth with the equatorial plane. Now, our angle, it is denoted as omega. It is the angle through which earth has to turn to bring the meridian of the observer directly in line with sun's rays. It is an angular measure of time. This is the angle in degree which is traced by the sun in 1 hour with reference to 12 noon of the location, and the convention of measuring it is that noon based calculated local apparent time. It is positive in afternoon and negative in forenoon. Here the earth completes 1 rotation in 24 hours. Hence, 1 hour corresponds to 15 degree of Earth's rotation. So, you can see in this figure the hour angle, which is an angular measure of time. At solar noon, the sun rays is in line with local meridian or longitude. The hour angle at that instant is 0 and it is calculated as solar time minus 12 into 15 degree. So, this is the hour angle. The next is the inclination or altitude angle, which is denoted as alpha. It is the angle between sun's ray and its projection on horizontal surface. Zenith angle, which is denoted as theta z, is the angle between sun's ray and normal to the horizontal plane. There is another angle, solar azimuth angle. It is denoted as gamma s. It is the angle between projection of sun's ray to the point on the horizontal plane and line due south passing through the point. The value of this azimuth angle is taken positive when the measurement is done from south towards the west. Angle of incidence is denoted as theta. It is the angle formed between direction of the sun ray and the line normal to the surface. The tilt angle is the angle between the inclined slope and horizontal plane. Surface azimuth angle is the angle in horizontal plane between the line due south and horizontal projection of normal to the inclined plane surface. Normally, this is taken as positive when measured from south to west. So, the basic sun-earth angles are latitude, declination angle, hour angle, inclination angle, zenith angle, solar azimuth angle, angle of incidence, tilt or slope angle and surface azimuth angle. Now, we will see the angle between the incident beam and normal to inclined surface, that is denoted as theta. The angle of incidence can be estimated as cos theta is equal to sin lambda multiplied by sin delta cos beta plus cos delta cos omega sin beta. Let's find out the local apparent time, how it is calculated. Local apparent time, abbreviated as LAT, it differs from place to place and it depends on longitude of the place. So, the sun rises in the east and any location in the east will have earlier sunrise and earlier sunset. So, it is the time used to determine hour angle. It is determined from standard time by applying two corrections. The first correction is needed due to difference between longitude at the location and longitude of the place whose standard time is used for calculation. 15 degree or 15 longitude is equal to 1 hour. A correction of 4 minutes per longitude difference is given to the standard time. And the second correction is called time correction, which is needed as both Earth's orbit and rate of rotation are subjected to small fluctuations. So, we can find out the local apparent time by this equation. It is standard time plus or minus 4, that is standard time standard time longitude minus location longitude plus equation of time correction. So, by this way we can find out the LAT. Normally, the negative sign for LAT is used for the eastern hemisphere and positive sign for the western hemisphere. Let's calculate the hour angle for local apparent time like 6 am, 9 am, 12 noon, 3 pm, 6 pm and 9 pm. Hour angle is given by omega is equal to solar time minus 12 into 15 degree. So, if the solar time is 6 am, omega is equal to 6 minus 12 multiplied by 15 degree, which is equal to minus 90 degree. And at 9 am it is minus 45, 12 it is 0 and 3 pm it is 45 degree, 6 pm it is 90 degree and 9 pm it is 135 degree. So, if you know the solar time, what is the time, exact time, you can find out the hour angle. Let's do another problem. Determine LAT corresponding to 1500 or that is IST in IST at Mumbai. It having latitude longitude of 90 degree 7, 75 degree 51 east on 1st July. In India, the IST is based on 82.50 degree east. On 1st July, the equation of time correction is equal to minus 4. So, here you can apply that equation. Lat is equal to time plus or minus standard time longitude minus location longitude, which is multiplied by 4 minutes plus equation for time correction. So, we can see it is 15 hour. So, 1500 minus 4 into 82.50 minus 72.85 minutes minus 4 minutes. Then you will get around 1417.4 hour. Now, we will see the sunrise, sunset and solar day length. At sunrise, the sun rays propagate parallel to the horizontal surface. So, the angle of incidence and zenith angle are equal and have a value of 90 degree and the corresponding hour angle is equal to the cos theta which is equal to cos 90, or you can say it is equal to cos lambda cos delta cos omega plus sin delta sin lambda. Cos omega is equal to minus tan lambda tan delta, or omega is equal to cos inverse 1 into minus tan lambda and tan delta. Similarly, the sun rays are parallel to horizontal plane during sunset. So, this is at the sunrise, and at the sunset, and the hour angle is minus omega, which is equal to cos inverse 1 minus cos inverse 1 multiplied by minus tan theta tan delta. The angle between sunrise and sunset or the solar day length is given as. So, that is the angle between sunrise and sunset is the solar day length, and it is denoted as 2 omega, which is equal to 2 multiplied by cos inverse 1 of minus tan lambda tan delta. Normally, the sun traverses 15 degree in 1 hour, and the sunshine is available between sunrise and sunset, and that is the solar day length, and the duration is measured in sunshine hours, that is TD or daylight hours. It is given as TD, and it is estimated as TD is equal to angle between sunrise and sunset divided by 15 degree multiplied by 1 hour. So, 2 omega by 15 into 1, which is equal to 2 by 15 into substitute the omega value, cos inverse 1 minus tan lambda tan delta. The latitude angle increases from the equator to poles, and day length hours will increase as we move towards pole. We can see the change of day length hours with latitude, change of day length hours with this latitude in this figure. Let us calculate the number of day length hours in Srinagar for 1st January and 1st July. Here the latitude of Srinagar is 34 degree 5 minutes north. Declination angle lambda is given as 23.45 multiplied by sine of 360 by 365 multiplied by sum of 284 plus n, and n is counted from the 1st January. So, 1st January n is equal to 1 because it is 1st January. So, the number of days of the year counted from 1st January 1, and delta is equal to 23.45 multiplied by sine of 360 by 365 into 284 plus 1, and the value you will get is minus 23.01 degree, and TD is calculated as 2 by 15 cos inverse 1 minus tan lambda multiplied by tan delta, which is equal to 2 by 15 cos inverse 1 minus tan of 34.08 multiplied by tan of minus 23.01, and you will get 9.77 hour. So, it is the daylight hours during 1st January. In 1st July, the n is 182, that is this many days from 1st January, and you substitute that n delta is equal to 23.12, and the day length is equal to 14.24 hour. So, you can see at 1st January the same place has different day length from 1st July. Let us calculate the intensity of terrestrial radiation. The radiation reaching from extraterrestrial region to the earth's surface is normally known as the beam radiation. This intensity of beam radiation normal to this direction of beam's propagation is called normal intensity, and it is given by Ix multiplied by exponent of minus Tr by 0.9 plus 9.4 sin alpha, where Ix is intensity of extraterrestrial radiation in the direction of radiation, and Tr is the turbidity factor. Normally, this turbidity factor depends on months and types of region. The normal intensity In and the intensity normal to horizontal surface is given in this figure, and the beam radiation and diffuse radiation on horizontal surface is given by Ib is equal to In cos theta z, and Id, that is the diffuse, this is the beam radiation. Ib intensity of beam radiation is equal to intensity of the normal multiplied by cos theta z. Id is equal to 1 by third of Ix minus In multiplied by cos theta z, and the total or the global radiation consists of these two radiation and reflected radiation. So, it is given as Ig, intensity of the global radiation, is equal to Ib into Rb plus Id into Rd plus Rr multiplied by Ib into Id, where Rb, Rd, Rr are the conversion factors for beam radiation, diffuse radiation and reflected radiation. Solar radiation data. It is important to design the solar energy system, and it is necessary to know the monthly average and as well as daily solar radiation data on the horizontal surface consisting of both the total, that is the global and diffuse radiation, and also daily solar radiation data with certain tilt angles. The monthly average of daily radiation is obtained by averaging daily radiation for the month. That means if you add all the daily radiation and divide it by the number of days in the month, you will get the monthly average of daily radiation. It also depends on the tilt of the surface, and it depends, the monthly average radiation depends on hourly variation of global as well as diffuse radiation, amount of radiation received per day, the number of sunshine hours per day. The availability of solar radiation can be obtained with the help of solar radiation maps, and normally these are drawn to show the distribution of annual mean global radiation. You can see a solar radiation map in this figure. Let's do the monthly average daily global radiation on horizontal surface estimation. This is determined by or determined from monthly average daily extraterrestrial radiation, that is H0 bar on horizontal surface, and monthly average daily hours of bright sunshine, that is N bar, and monthly average of maximum possible daily hours of sunshine, that is capital N bar. So, here Hg bar is the global radiation. So, Hg bar by HO, that is on horizontal surface extraterrestrial radiation, is equal to A plus B multiplied by N dash by small n dash by capital N dash, where A and B are regression parameters. Normally it is constant for a particular location. So, this is the monthly average daily global radiation on the horizontal surface. If we need to calculate it for the monthly average daily diffuse radiation on horizontal surface, it is estimated as, or it is given by the equation HD bar by Hg bar is equal to 1.194 minus 0.838 KT bar minus 0.0446 small n dash by capital N dash. This is the ratio of monthly average of daily global radiation to the monthly average of daily extraterrestrial radiation, and the monthly average daily global radiation on tilted surface, that is HT bar, is calculated as HT bar is equal to Hg bar minus HD bar. That means this is the difference of the global minus diffuse. So, a tilted, you can get the radiation at the tilted surface can be estimated by multiplying this conversion factor for monthly average daily beam radiation to the difference of Hg minus Hd plus Hd bar into 1 plus cos beta by 2 plus Hg dash rho multiplied by 1 plus cos beta by 2, where beta is the slope angle or the tilt angle. Estimate the average daily global radiation on horizontal surface at Baroda, which is having latitude of 22 degree north, 73 degree 10 minutes east, during the month of March if the average sunshine hour per day is 9.5. Here assume A is equal to 0.28 and B is equal to 0.48, and also assume that H0 is equal to H0 bar, that is the average. This bar means it is the average. So, the average daily global radiation Hg bar on horizontal surface depends on monthly average of daily extraterrestrial radiation, that is H0 bar. According to the relation, Hg bar by H0 bar is equal to A plus B into N dash small n dash by capital N dash. N dash is the monthly average of sunshine hours per day at the location, and capital N is the monthly average of maximum possible hours per day at the location. So, for this, first you have to start with delta, that is declination angle. It is estimated as 23.45 sine of 360 by 365 into 284 plus n, and for 16th March the value of n is equal to 31, that is the number of days from 1st January, it is 75 days, that is 31 in the January, 28 in the February and 16 days in the March. So, you will get 75 days. So, n value is 75. So, substituting that value, delta is equal to 23.45 sine of 360 by 365 into 284 plus 75, and the value is minus 2.42 degree. Now, the sunshine hour angle is given by omega, which is equal to cos inverse 1 minus tan lambda multiplied by tan delta, which is equal to, or substituting the value, you will get cos inverse 1 of minus tan 22 multiplied by tan of minus 2.42, which you got as the declination angle. So, you will get an hour angle of 89.02. Now, the day length, it is given by the n dash, capital N dash is equal to 2 by 15 multiplied by omega. We apply this or substitute this value of omega. So, you will get 2 by 15 into 89.02, which is equal to 11.87 hour. Now, the H0, which is equal to 24 by pi multiplied by ISE multiplied by 1 plus 0.033 cos 360 n by 365, which is multiplied by omega sin lambda multiplied by sin delta plus cos lambda cos delta sin omega. Applying or substituting the values, you will get 11,911. Now, Hg bar by H0 is equal to A plus B multiplied by n bar by small n bar by capital N bar. Now, all the values are known. So, you substitute this 0.28 plus 0.48 multiplied by 9.5 divided by 11.87. You will get 0.664, and the global Hg dash is equal to 0.664 multiplied by 11,911 kilojoule per meter square. So, now you know how to calculate the day length. If the latitude is given and declination angle is given, you can find out easily the day length. Let us find out the sunrise and sunset hours and this day length for solar and also the solar altitude angle at 2 hour after local solar angle on 1st June for place located at a latitude of 26.75 degree north. So, first we will start with small n, that is the number of days. So, it's 1st June. So, you will get 152 days. So, n is 152. Then the delta, the inclination angle, you will find out with the equation which is given 23.45 multiplied by sine 360 by 365 284 plus n, you will get 22 degree, and the hour angle omega you will get 30 degree from the equation 2 hour into 15, and sine lambda is equal to sine alpha is equal to sine lambda sine delta plus cos lambda cos delta cos omega. So, substituting this value, you will get alpha is equal to 72.4 degree, and TD you can apply this to the equation 2 by 15 cos inverse 1 minus tan lambda multiplied by tan delta. You have all the values substituted. 2 by 15 cos inverse 1 minus tan 26.75 multiplied by tan 22, you will get 10.4 hours. Sunrise is at 12 minus 10.4 by 2 hour, that is you will get 6.8 hour, which is equal to 6 hour 48 minutes, that means 6:48 am. And sunset you have 5.2, 12 plus 5.2 hour, you will get 5:12 pm. So, the sunrise at that location is the latitude of 26.75 degree north is 6:48 am sunrise and 5:12 pm sunset. Now, how you will measure this solar radiation? This is mainly measured with the help of pyranometer, pyrheliometer, and sometimes the sunshine recorder is also used. Pyranometer is a radiation energy measuring device that is used to measure global or total radiation, usually on a horizontal plane, but it can also be used to measure an inclined plane. Pyrheliometer is used to measure beam radiation. If you want to measure the beam radiation, you should use pyrheliometer. And the sunshine recorder is used to measure the duration of the bright sunshine hours in a day. So, the radiation quantity or the intensity is measured by pyranometer or pyrheliometer, while the duration of bright sunshine hours is in a day is measured by sunshine recorder. We have seen the difference between the radiation, that is beam radiation and diffuse radiation, and how to calculate the solar radiation and how to measure the solar radiation. So, to summarize this module, we have seen that the radiation spectrum of sun and earth is differ. Mainly the sun's rays radiation is short wave radiation, while the earth's radiation is long wave radiation. We have seen different angles between the sun and earth, like the latitude, we have seen the inclination angle, we have seen the hour angle, we have seen zenith angle, tilt angle, etc., and how these are to be calculated. We have also seen how to estimate the intensity of terrestrial radiation. We have seen how to find out the local apparent time, and also if the latitude is known, what time for the sunrise and sunset for that particular area. We have seen that radiation are of two types, mainly the direct radiation and the diffuse radiation, and the total or the global radiation is the summation of beam radiation or the direct plus diffuse radiation and the reflected radiation. And we have seen the solar radiation data, how it should be measured, or how it should be, what is the importance of this measurements, how to calculate the average daily global radiation, average daily diffuse radiation, and as well as the average daily global radiation on the tilted area. So, we have seen the different instruments which are used for the solar radiation estimation, like pyranometer, pyrheliometer. Thank you.